Hello, my name is Franck Dary, and I will present to you the work I've done with my two PhD advisors Alexis Nasr and Abdallah Fortazi for Coxside 2021 on the role of low-level linguistic tasks for reading time prediction. In NLP, short form Natural Language Processing, we use tools to build a structured linguistic representation out of raw text. And this structured representation is made of some linguistic layers. Here, in this paper, we will work with 6 standard linguistic tasks, which are tokenization, part-of-speech tagging, morphological tagging, lemmatization, dependency parsing, and finally, sentence segmentation. Those tasks are ranked here from low level to high level, in the sense that high-level tasks depends on lower-level ones. For example, dependency parsing depends on word segmentation, and often assume part-of-speech tagging. When a human is reading a text, it is also building a structured linguistic representation of this text inside his mind. But this representation is built subconsciously, and the resulting structure is probably very different than the one we are dealing with in NLP. And when the human is reading the text, it is doing so in an incremental fashion, meaning that for each word that is being discovered, the word is immediately being integrated into the current representation of the meaning of the sentence. And so there are some words that are much more difficult to integrate into the current representation than others. It can be because the word is rare or simply because the word is very surprising in the context. So in this work, as it has been done before, we will use total reading time on each word to approximate the difficulty it was for the reader to integrate this word into the representation. What about our NLP tools? They are based on the transition-based parsing algorithm, meaning they are greedy. And so in this setting, processing a text is akin to predicting a sequence of action where each action will discover a new word or integrate this word into the current representation. And so, for each word, we are able, for each linguistic level, to produce a complexity metric estimating the difficulty that the NLP tool had to process this particular word at this particular linguistic level. And so the scope of this work is to compare the complexity metrics we will obtain with our NLP tools with the complexity metrics that will be estimated by looking at the total reading time of human readers on the same text. So what we'll be doing is we will take some text that has been read by human readers. We will give this text to NLP tools that will be asked to build a representation of this text, and by doing so we'll produce for each word and each linguistic level a complexity metric. On the other hand, the human readers will produce a complexity matrix that again will be the total reading time for each word, and we will compare the two. The questions we ask ourselves are: is there a correlation between word level difficulty of human reader and NLP tools? And if so, for which of the 6 linguistic levels? And then we will compare 2 settings of our NLP tools to see which one is more correlated to human behavior than the others. Now, let's take a look at how we are producing the complexity metrics for our NLP tools. Let's take, for instance, part-of-speech tagging, which is one of the 6 linguistic tasks we are dealing with. So in this setting, in the greedy setting, parse tagging is simply for each word of the sentence selecting one action out of 17, the action being the possible part of speech. So the system for each word will predict a distribution of probabilities over the different actions, and then it will simply select the most probable one. And so out of these distribution of probabilities, we can extract 2 different complexity metrics, one being surprisal which has been used a lot in the literature before, which is simply the negative logarithm of the probability of the chosen action. The chosen action being the most probable one. And then we define entropy as being simply the mathematical entropy of this distribution of probability. And we argue that entropy, because it uses all of the probabilities and not only the most probable one, is more suitable to take into account an hesitation of the system between multiple actions. Then we will oppose two strategies for producing the complexity matrix. The first strategy, that we call non-incremental, is the standard way to do things in NLP. It is also called sequential or pipeline. And in this kind of architecture, we process every word of the text at a certain linguistic level before changing to the next linguistic level. So, for instance, here we have the processing of the sentence, "The boy hits the ball." And we are currently predicting the blue square. So this is the morphology for the word hits. And you can see that when we are doing this, we already have processed the whole text for the lower levels, so for part-of-speech tagging and tokenization. But we haven't even started on sentence segmentation or dependency parsing. And so this way of doing things in pipeline is very far from the way a human will be processing the text, because in this non-incremental strategy, the whole text is being read multiple times, each time for a certain linguistic level. In opposition, we have the incremental strategy, in which each word, when it is discovered, is treated at each linguistic levels before switching to the next word. So if we take the same example of the processing of the sentence, the boy hits the ball, when predicting the blue square, we can see that we have no information about the right hand context prediction yet, because we haven't even discovered yet the words the and ball. But we can see that for the left hand context, we already have started lemmatization, dependency parsing, and sentence segmentation. And so this incremental way of processing text is arguably, in our opinion, much more cognitively plausible than the other one. And so for the rest of the paper, we will argue that it is the case and that it will produce better complexity metrics. Now, let's take a look at the data we used for our experiments. We used the Provo corpus, which is a recording of eye movements of 84 skilled readers, each reader reading about 3,000 words. So what we've done is that we've taken the text of the corpus, fed it into our two different NLP tools, and each tool is producing for each word two complexity metrics, entropy and surprisal, for each of the 6 linguistic levels. We've taken all of that and then merged it with the Provo corpus, resulting into a big matrix of data. Here we can see an example of this matrix where you have the words. For each word you have the readers, the reading time of the readers, and then the complexity metrics for each linguistic levels produced by our NLP tools. In our experiments, we decided to fit 5 different linear mixed effect models on the total reading time on each word, using not only base features like frequency of the target word, the frequency of the next word, and the length of the current word, but also our complexity metrics produced by our NLP tools. So we have one complexity matrix for each of the 6 linguistic levels, and we have surprisal and entropy, each one produced by the incremental NLP tools and the non-incremental NLP tools. And then we will find out which model fits the best. So we defined 5 different linear mixed effect models. So we have one model that is named vanilla, and that is not using any complexity metrics as feature, only baseline features. And then we will compare it to models that use all the features from vanilla and then a combination of entropy or surprisal with incremental or non-incremental tools. And as random effects, we use a nested participant per sentence. Now let's take a look at the results. So we fit our 4 models using complexity metrics, and here we have the resulting models. So the rows, except for the first, are the features of the models. The first rows are the complexity matrix feature, and the bottom rows are the baseline features, and the columns are the models. So the model that is the most interesting to us is the second column here, because it is the entropy metric computed by the incremental NLP tool. So what we can see on all the table is that every value is quite significant, except for the grayed out cells. Especially the lemmatization is not really significant, and it is kind of logic because we used English language in our experiments, and lemmatization is not very interesting in English. What we can see also for the column that is most interesting to us is that the coefficients have the right sign because the complexity matrix coefficients are positive, meaning that a high complexity is resulting in a high reading time, which is what was expected. Now, what we have done is that we have done a pairwise comparison between all of our 5 models, including the baseline models, vanilla. So in this table, what you can see is that on each row there is model 1 that is compared with model 2, and model 2 is always better than model 1. The models are compared on their ability to feed the data being the total reading time on each word, and this comparison is made using the AIC of the model on the data. So the AIC is like a likelihood, but with a penalty for having too many parameters. So what we can infer from this table is that we have the following order on the model. So the best model is the model using the complexity matrix entropy produced by the incremental NLP tool. And the worst model is vanilla. So what we can see is that all of the complexity metrics are an improvement over the baseline features. And what we can see also is that incremental models are always better than non-incremental models. And what we can see also is that the entropy is a better complexity matrix than surprisal. So to summarize, what we have done in this work is we have developed a text processing pipeline that is taking raw text and building a structured representation over 6 linguistic levels. And we have done so in 2 different settings, an incremental setting and a non-incremental setting. And so there's NLP tools were able to produce word-level complexity metrics for each word. We have tested 2 different complexity metrics, surprisal and entropy. And what we can conclude out of that is that the complexity metrics are helping total reading time modeling in every case. Also, the complexity metrics produced by incremental models, so more psychologically plausible models, are better predictors of total reading time. And also, we found out that the entropy is better than surprisal in this case. Okay, thank you for your attention, and if you are interested, do not hesitate to ask questions. I'm sorry if it wasn't very clear, but due to time limitation, I had to go fast on certain details. So thank you and have a nice conference.